Hello, everyone. My name is Dennis Trujillo, and I'm glad to introduce you to the first RCIF Applied AI seminar series. Today, we'll be talking about deep learning model optimization with PyTorch. So let me just jump in and talk about the anatomy of a neural net to get started. So any neural net that we'd be training in PyTorch comprises a few key components. So we have the input layer. The input layer is the first layer that the data is going to be passed through. This is where we are basically taking features and we're representing them. We have the weights, which are the parameters that are learned during the training process. So they are basically the representation of the input signal, basically turning on and off different neurons. We also have the optimizer, which is a key component of the neural net. So it's an algorithm that is used to adjust the weights of the connections within the network to minimize the loss function. So we have input data, which is being learned through the neural net, which is a universal function approximator. And we have an output target that we're trying to minimize the loss in respect to. So some examples of the optimizers include stochastic gradient descent, atom, and RMS prop. Beyond that, we have the activation function. So this is where the nonlinearity comes in that actually makes a neural net useful. So we have nonlinear functions that determine the mapping of input to output. So we have ReLU, sigmoid, and tanh. So depending on how you scale your inputs and outputs. If the outputs are between 0 and 1, you would use ReLU. If it was between -1 and 1, you would use sigmoid and tanh. So it really depends on how you're scaling your data, but this is how we introduce nonlinearities and really give power to the neural net. And the loss function is what we're trying to minimize. So we have inputs, we have outputs, and we have the universal function approximator, and we have the loss function. That's what we're trying to minimize at the end of the day. So there's simple loss functions like a mean squared error for regression or cross entropy for classification tasks. And then we have the output layer. So the output layer is the final layer in the neural net, which produces the model's prediction. It's tailored to the specific type of problem being solved, such as for classification or regression, you may have a continuous series of numbers for a regression task, or you may have specific classes for a classification task. So I'm going to jump into best practices when structuring a training loop now. So a few things to keep in mind is you want reproducibility. So it's really important to set deterministic behaviors with fixed seeds at the beginning of your code. It's also very useful to use built-in data sets and data loaders. So those classes make handling batch-wise data with multi-processing much more efficient. You also want to make sure that you choose the appropriate optimizer for your problem. And beyond that, you want to separate your training and validation loops and enable gradients on and off as necessary, dependent on whether you're in the training phase or validation phase. It's also really important to utilize real-time monitoring with logging like TensorBoard or the built-in tools within PyTorch to track metrics like loss and accuracy. Another very important key component that I would recommend is utilizing checkpointing. So checkpointing is a way of saving your model state within or during the run. So each time the loss is minimized, ideally you would save your model state and keep that model for later in case you need to restart training. So I'm just going to show a quick example here of how you would go ahead and set seeds at the beginning. So these are some code snippets. There's going to be more formal code available to everybody at the end to get started. So that will be available on the cluster in a GitHub repo. But this is how you would set a seed. So you want to seed everything, essentially. So this is how you can go ahead and set a bunch of different seeds and make sure that those are all set when you begin your training loop. It's also really important to use data loaders. So data loaders make it really easy to take a data set. Let's say that you have a bunch of images that you're loading in using a built-in class within PyTorch, or let's say you have a self-defined data set. So it's really important to use a data loader because this makes working with data much simpler, because you can load data batch-wise and process data parallelly when you're doing pre-processing of data. So this is an example training loop. So we see the key components. So we're running it for a number of epochs. We have the inputs and the labels that we're sending to the device. We have the outputs that are basically what's coming out of the model from the given inputs. We have the loss function, and we're optimizing so we're optimizing and then passing backward, and then taking a step with the optimizer, and we're keeping track of the training loss. So these are some key considerations when training your model. In the train mode, in the validation mode, we switch to val mode. So we're now utilizing model.eval, and we're actually going and we're taking the validation set and we're passing that through, and we're looking at the output from the model, and we're saving that, and we're checkpointing by saying if the validation loss is lower than the best validation loss, and we want to save the model. So these are some good practices. Definitely recommend saving your model, doing checkpointing. That way you can pick up from that state later if you want to continue the training process, like if your job runs out of time, etc. So I'm going to talk about another way to potentially optimize your models. So data types. Data types are a way to easily reduce your training time and your memory overhead. So you can reduce your memory usage by using lower precision data types, which decrease the memory footprint. So this would allow for larger models or bigger batch sizes within the same GPU. So for example, instead of using float 32, you can use float 16, or you could use a bfloat 16. So these are reduced precision data types, which should still allow you to capture most of what you're trying to learn. So beyond that, modern GPUs and hardware accelerators are optimized for lower precision. So some of the A100 systems that we have would be better suited for utilizing lower precision data types. So they're optimized to train with those. Another way that you can use mixed precision is utilizing a combination of lower and higher precision data types through automatic mixed precision features. So you can use AMP to automatically adjust the precision of your data types as you're training. So by using smaller data or reduced precision data types, you can reduce data transfer volumes and enhance the overall data throughput and efficiency of the models. This is also a key consideration for doing inference, because lower precision operations are more power efficient. So this is a consideration for extremely large scale models or efficiency at inference. And we can see here at the bottom, so this is the speed up that you get by going from floating point 16 from FP32 to FP16. So you can see that for most models, like for example, ResNet, which would be most relevant to most people here, you get a 2x speed up. So you can get a 2x speed up in terms of training time. And in terms of considering the architectures, we see that for V100, utilizing mixed precision, if we go from floating point 32 to floating point 16, we can see an 8 times speed up. And then if we look at how it performs on an A100 system, we see significantly more throughput increase with reduced precision. So this is how you can actually utilize automated mixed precision within PyTorch. So you simply just need to add one line at the beginning before your training loop, and then utilize the scaler. So again, there will be full code provided on how to utilize each of these, which will be available on the cluster and which will be available in GitHub as well. So parallelization is probably the best thing that any of the models can utilize to try and improve throughput and training efficiency. So data parallel is one class that can be used. So you can parallelize across multiple GPUs. So data parallel allows for distributing the input data across multiple GPUs. This is a single node based tool. So data parallel is best used for running on a single node. If you want to train on a single node, then data parallel is probably your go-to. If you want to train across multiple nodes, there's other tools that I'll talk about later on. But utilizing data parallel would allow you to use multiple GPUs available on the node, which would enable processing speed ups and training time reduction by utilizing the computational resources more efficiently. So data parallel provides automatic splitting of the data. So it splits a batch of the input data and sends that to different GPUs and then aggregates the results on the primary GPU. So this simplifies the implementation of multi-GPU training and makes it really easy to use. Again, this is another one-liner type of addition to your code, which can make it much faster. So it's really straightforward to use. And there are some limitations to scale. This is good for small to medium-sized projects. Other tools may be more useful for larger scale projects, like if you're training across multiple nodes or training very large models with many GPUs. So again, this is best suited for single node training, and this is probably best suited for most people at the CHPC. So this is an example of how to implement data parallel. So basically, we're just wrapping the model with torch.nn data parallel, and then we send the model to device. So it's a few line add, and it can improve the efficiency of your training. So for multi-node training, you want to be utilizing distributed data parallel or a fully sharded data parallel. So distributed data parallel, DDP, in PyTorch is optimized for multi-GPU and multi-node training. So it's highly scalable and efficient for large-scale machine learning projects that require substantial computational resources. So let's say you have a very large imaging model that you want to distribute across multiple nodes. Distributed data parallel would be a go-to solution. So again, it facilitates communication between multiple nodes and multiple GPUs, super easy to use. So it's a single program with multiple data points that are shared across all of the nodes and all of the GPUs on those nodes, and then it's aggregated back to the main GPU. So it's robust and fault tolerant. It has features to handle failures and restarts. So it's pretty robust. Once you get it running, it can be useful. There is some overhead, though, in terms of communication. So anytime you need to communicate with multiple nodes, you're going to have a communication overhead. So there may be some limitation in terms of speedups for certain problem sizes. So again, this is a small snippet on how you can implement distributed data parallel within your own code. And there will be code examples provided on the cluster and in GitHub to show how to utilize all of this more fully with ResNet 18. So something which has been released more recently is fully sharded data parallel, so FSDP. So this is even more efficient and distributed data parallel. So it's specifically designed to reduce memory usage by sharding the model parameters, optimizer states, and gradients across all available GPUs. So you can train much larger models this way than typically possible with traditional data parallel methods. So basically, this is a way of making it much more easy and much more distributed by sharding all of the considerations, all of the model components across different nodes. So it automatically reconstructs the full model state when necessary, such as at checkpointing or evaluation. So it handles the complexities of parameter gathering and scattering, it simplifies the process overall. So it's designed to scale efficiency across multiple GPUs and across multiple nodes. So it's a very scalable tool, and it integrates mixed precision training. So it seamlessly integrates with AMP, like we talked about earlier. So you can use AMP with fully sharded data parallel. And again, here is an example of utilizing fully sharded data parallel, and there will be some code examples with submission scripts provided for all of this. Profiling. So just to talk about profiling, there's a couple of different profilers that are available. If you're interested in utilizing profiling through TensorBoard, I can also walk anybody through setting that up. It's pretty simple in terms of logging that data back to TensorBoard. And there's other tools within PyTorch that are available, or there's tools from Determined AI, which we can also demonstrate, which make profiling models fairly simple. So just to compare DP versus DDP versus FSDP, so just to consider all of the different features, main takeaway that anybody here should probably consider is data parallel is best for single node training. Distributed data parallel is good for multi-node training, but the very best for multi-node training is probably going to be fully sharded data parallel for the most efficient multi-node training. And you can see all of the features for each of those techniques here. Another consideration at inference is just-in-time compilation. So if you want to have a model which runs really efficiently at inference, not necessarily quickly during training, let's say you have your model trained or you have a technique nailed down for training your models efficiently. Let's say you want to make your models available for use in a very efficient and quick way at inference time. So you can do just-in-time compilation. So a just-in-time compilation optimizes the computational graph, which merges operations and eliminates unnecessary computations. So it kind of prunes and reduces the size of the model to make it much more usable during inference time. So this could be useful, like let's say you trained a really complex model and you actually wanted to deploy it on a small device like a phone or a small computer to be used in a clinical setting. So it reduces the execution overhead by compiling the model into lower level language as well. So it prunes and compiles into lower level language, and it enables cross-platform deployment by utilizing Torch script models. So this really makes it easy to take a model which was trained on GPU, like a big GPU model, and then reduce its size and deploy it on something much smaller. Quantization is another consideration. So this kind of gets back to the idea of looking at data types. By reducing data types, the way we talked about earlier, that's probably more efficient. Quantization is a way of reducing inference time and making the model more efficient at inference. It's not really useful for training because it actually adds computational overhead at the train time, but it reduces the memory footprint, the computational demand of the neural net by converting the model weights and activations from high precision float32 to even smaller representations like int8. So for example, it's kind of like a way of rounding numbers. So you're taking something which is float32 and you're mapping it to int8, making the model much smaller. This is a way to really take your models once they're trained and ready to go and making them as small as possible. So this helps with enhanced inference speed by leveraging lower precision arithmetic. This is really going to make it as fast as possible to run your models on a small device and make them available to users in the field. So there's applications for using this in transfer learning. Let's say that you took a ResNet 18 model off the shelf and you wanted to use it. So you could take those model weights, you could train or fine tune a model, and then you could quantize that model down to make it super small. Or you could take a larger model, any model essentially, and train it and then quantize it, make it available for inference. So this can be done a couple of different ways. There's post-training quantization, which allows for applying quantization after the model has been trained and fine-tuned. So that is like another one-liner, or you can use quantization-aware training, which basically incorporates quantization at the training level and makes it, it adds some overhead, but this is another way of doing it. This would make your model very small and very efficient. So this is an example of defining a quantized model. So this is a simple CNN where we're actually implementing the quantization step, the dequantization step, using quantization-aware training. And that's it actually from my side in terms of different techniques for optimizing neural nets. Happy to take questions from everybody, and there will actually be a lot of code tutorials available for everybody as well. Actually playing with this hands-on, and some Google Colab notebooks as well. I'm happy to answer any questions, and I would also like to invite everybody to sign up for next seminar, which is going to be on best practices for parallelization on CPU and GPU.